Okay, kids, we're back and we're moving on to section 7.9 in the textbook. It's all about beat frequency. It's a really neat phenomenon. So, what I need you to do before we continue with today's lesson and note here is in our announcement, in our announcement, there's this link right here. Beat frequency video 1. Watch this video first. If you watch this video first, then you'll have a much better understanding of the note that we're going to go through. So stop this video that you're watching right now, my little lesson video. Click on this link here. It's a YouTube video. He's a professor uh, who does something very similar to what I would have done in the classroom. So that's why I'm using some of these videos. I kind of see, I think, similar to this fella. So watch that video, then come back to the note. Okay? All right. So I hope you watched that video. Beat frequency. It's still an interference phenomenon. It still involves two waves, in this case, two sound waves. And they're interfering, but things are a little bit different now because the two waves that are coming together to interfere don't have the same frequency, don't have the same wavelength. They're very close to each other. And that's what caused the phenomenon that I hope you watched in the video I suggested you to watch. So you get the result of the interference is what we call a series of beats. Well, what's a beat? A beat is a sequence of loud and soft sounds. Loud, soft. So one beat is equal to loud, soft, loud, soft, loud, soft. Each loud, soft is a beat. So let's say, like in the video, we have two tuning forks and we play them together and you hear a loud, soft, loud, soft, loud, soft. That means you hear 1, 2, 3 beats. And let's say you hear those 3 beats in 1 second. Well, there's an equation that will let you calculate what the beat frequency is. Frequency, beat frequency, is equal to the number of beats divided by how much time it took for those beats to occur in. So frequency beat would equal 3. There's no unit, you're just counting something like 3 apples, 3 oranges, 3 beets. I don't mean the kind of beets you eat. How much time did it take? 1 second. So that is equal to 3 over a second, or 3 times inverse seconds. But we know that inverse seconds, from a long time ago, we looked at this, that's 3 hertz. So if you ever are given two tuning forks of slightly different frequencies, you could measure the beat frequency that is produced by the two of them. So that's kind of cool. There's another equation that will let you calculate the beat frequency. Frequency, beat frequency is equal to absolute value signs. These are not brackets. These are absolute value signs. So whatever you put in here, you eventually will write out a positive value. Even if the subtraction, the difference is negative, you get a positive value out of it. So let's do an example. Let's say you've got a tuning fork and you know it's operating at 440 hertz. Another tuning fork number 2, is operating at 444 hertz, and you would want to find the beat frequency that is produced when these two are played together and they interfere with each other. So here it is. Frequency beat is equal to absolute value of, see, absolute value sign, a subtraction of the two frequencies. So it would be 440 minus 444. Subtract these hertz, and you'd think, well, sir, that's negative 4 hertz. Well, but you've got absolute value signs, so the answer is 4 hertz, which is telling you that the two sources are 4 hertz apart from each other in the sounds that they are being produced. Okay? Now look, what we're going to do now is I'm going to show you some online computer simulations of beats to help you see this. I've put the links to these on the website, today's announcement as well. So that's what we're going to do next. So here is a simulation. I put the link in today's announcement. So here's one wave. It's represented by the blue wave. It's operating at a frequency 1 of 250 hertz. And exactly same time and exactly same place, another sound wave is being produced. So your ears will also hear this one, frequency 2 at 270 hertz. And what you would hear is the constructive and destructive interference that is produced when these two waves are at the same place at the same time. They're going to interfere with each other. So let's overlay them. And you see that at some points where your ear is, because the waves are moving towards your ear, at some points in time, the crests and the troughs will be roughly aligned with each other. So you'll get a lot of constructive interference. But as time goes by, your ear stays in the same place, but the waves that are approaching you now, they are out of step with each other. And look, you'll have crests and troughs, meaning that's destructive interference. And you will get a beat frequency produced. And this beat frequency, if you remember the equation I gave you, would be 250, 270, they're 20 hertz apart. So you would hear 20 beats per second. Right, and you can zoom in here if you want to take a look at what's going on. All right, it's all, if you take a look at the bottom here, it's shortening up, changing the amount of time that you're listening. All right, but here's a beat, loud, soft, loud, soft. That's a beat, and you can play around with this. All right, you can maybe bring the frequencies closer together. There you go. That's trying to get 245. Come on, Mr. Z. That's close enough to 245 right there. Okay. And you can see now you'd only get about 5 beats per second, not as many. So play around with this simulation. It's kind of cool. All right. Now here's another simulation you can play with, and you can set the display to show one of the waves, both of the waves, but you always see what the two of them added together. So this is showing a 300 hertz frequency and a 305 hertz frequency played together. That's the sum. So I can either show the sum, the interference, or I can show one of the waves, or I can show the other wave, or I can show both waves together, or I can just show the sum. And you can also change the time available for you to look at these things. There you have it there. You can play around with that. Well, that's not helpful at all, but they're there. Okay, you can see these things. And what's really neat is you can play it. You can unmute it. And you'll hear the beat. And then what you can do is maybe change this from 305. How about we change it to 301? Press enter, and the beat that you hear changes. And you can also change the time that you are looking at this here. I want you to play around with it so you get a sense of a beat. So we went from 305 to 301. We'll do one more. 310. All right, a lot more beats per second, right? Because the difference between 310 and 300 is 10. So you're going to hear a lot more loud softs per unit time. That's a lot of loud softs per unit time. Okay, and you can play around with the view to help you visualize what's happening as you zoom in and out through time. So look at a lot of loud softs. Or you can, let's put a 2 in here. Let's see what happens. Oopsie. Let's see what that does. See? Fewer loud softs per second. Much different. So play around with it. It's the only way you're gonna get a sense of what a beat is. If we were in the classroom, I'd have a whole bunch of demos set up, kids. I'm so sorry we're not in the classroom. I miss all your smiling faces. I'm trying to do the best I can here. If you have any suggestions on how I can do this better or anything like that, please let me know, because I'm new to this too. And we'll do the best we can. Okay, you guys take care. Bye bye.